In module 4, you have to study about dispersion of air pollutants, plume dispersion theory, Gaussian plume model, its various assumptions, advantages and disadvantages, Pascal's stability curve, dispersion problems involving point source and line source, as well as estimation of plume rise. So to begin with, there are mainly two types of plume, that is continuous plume and instantaneous plume. Continuous plume, as you know from the term itself, it is continuous, so the sampling time will be very long. And in case of instantaneous plume, we will analyze the plume or for a particular time, for a particular instant, so that sampling time will be very short, as well as the release time will be very considered to be very short. And there are various types of plume rise, that is based on the factors affecting plume rise, that is buoyancy effect and momentum rise. Buoyancy effect means the rise due to the temperature difference between stack plume and the ambient air, that is once the effluent is emitted from the stack, the stack gas temperature will not be same as that of the ambient air temperature. So depending upon the difference in those two temperatures, buoyancy effect will be there, and due to that effect plume rise will happen. And momentum rise is another reason, that is due to the exit velocity of the effluents. Due to the exit velocity of the effluents, then momentum rise, plume rise can happen. And there are two formulas for buoyancy flux and momentum flux, which is given as F is equal to GVS into d square into delta t divided by 4ts, where F is buoyancy flux, G is acceleration due to gravity, Vs is the stack exit velocity, d is the exit diameter of the stack. Then delta T is Ts minus Ta, where Ts is the stack gas temperature and Ta is the ambient air temperature. And for momentum flux, the formula is Ta divided by Ts into Vs square into d square by 4. And all the terms are just the same as the previous equation. Now, moving on to the basic segments of an elevated plume, moving on to the various segments of an elevated plume, there are basically three segments. In the diagram, you can see basically three segments for an elevated plume. That is the initial phase, the transition phase, and the diffusion phase. And again, the initial phase is divided into three sections, that is the vertical jet section, the bent over jet section, and the thermal section. Okay, so jet section is actually the portion right from the exit of the stack. Okay, that is, you can see it, there is no dispersion happens in this jet section, just the plume is coming out of the stack or the chimney, so it is considered to be the releasing point. And after the jet section, the diffusion just begins to take place, that is just the cross flow will be rapid in this bend over jet section, and thereafter in the thermal section somewhat the diffusion just begins. Okay, and right in the transition phase, the diffusion happens due to the atmospheric turbulence, that is in the initial phase the dispersion just begins due to the internal turbulence in the effluent, but in the transition phase the internal turbulence level gets decreased or gets dropped out, and then the diffusion starts to take place only due to the atmospheric turbulence, and thereafter in the diffusion phase the complete dispersion of pollutant happens. So in the initial phase, there are three sections: vertical jet section, bent over jet section, and thermal section. And the vertical jet section, it is the release point of effluent from the stack to the atmosphere, and the pollutants are not dispersed immediately in this vertical jet section. Why? Because the ratio of why? Because only if the ratio of Vs to U, that is the stack gas velocity to the wind velocity, is greater than 4. And in bend over jet section, the cross flow will be rapid, and because of the internal eddies in that uh, emitted effluent or the emitted parcel of smoke. And in the thermal section, self-generated turbulence causes the mixing up of the pollutants, and it will further determine the growth of the plume. And in the transition phase, the plumes on internal turbulence gets dropped out, and atmospheric eddies or the atmospheric turbulence will completely determine the plume growth. And in the diffusion phase, the plumes on turbulence level gets phased out, and internal and the energy containing atmospheric turbulence, okay, and energy containing eddies of atmospheric turbulence will completely determine the plume growth. So these are the various segments of an elevated plume rise. Now moving on to the various coordinates of a plume. There are basically three coordinates, x, y and z. Here the x direction is usually considered along the direction of the flow, and y and z direction is along the vertical downwind direction, okay, and the other one is the y direction. Now moving on to atmospheric dispersion model. It's a mathematical model with the simulation involving the simulation of physics and chemistry governing the transport, dispersion and transformation of pollutants in the atmosphere. And it is one of the method of estimating, that is using this dispersion model one can estimate the concentration of pollutant in the ground, okay, or it will give information about the pollutant emissions and the nature of the atmosphere. So in many of the atmospheric dispersion models, mathematical models are applied, and application of three-dimensional parameters or the use of three-dimensional equations will often make the solutions uh, complex and difficult. And also here the concentration in all these atmospheric dispersion models, the concentration of pollutants are determined or estimated based on three coordinates, x, y and z. That is, x means the horizontal downwind direction, then y means the horizontal crosswind direction, and z is the vertical direction. And basically there are several types of models, air pollution dispersion models, okay. So they can be classified into three types, that is the deterministic models, the statistical models and the physical models. So deterministic models are actually those which involves numerical approximations in the solution of equations representing the atmospheric phenomenon. And also in the case of deterministic models, meteorological variables are required, data regarding the meteorological conditions are required, and such kind of models are usually used for long term decision making, that is for analyzing or predicting the pollutant concentration for a longer time period. Then second one is the statistical model, and that is in this kind of statistical model it uses empirical relationships between meteorological data and other parameters for predicting the pollutant concentration. And such kind of models are usually used for short term predictions, and only a little computational effort is required in statistical models. And the third one is physical models. So it's a kind of model in which a real atmospheric condition is simulated on a small scale in a laboratory. Okay, so in a laboratory, the real process will be simulated by means of some physical experiments, and the original condition or the original atmospheric phenomenon will be studied based on that replica. Okay, so it is this kind of physical model is usually used as a research tool to study specific atmospheric processes. So basically these are the three atmospheric pollutant dispersion models, and there are several other classifications based on the available time period, then based on the reactivity or non-reactive nature of the model, and also based on the coordinate system used, as well as based on the level of sophistication. Okay, so based on the time period, short term models and long term models are there. Then based on the uh, reactivity or the based on the nature of the pollutant, whether it is reactive, non-reactive or it is inert, depending upon that, non-reactive and reactive models are there. Then based on the coordinates used, grid based and trajectory based models, and also based on the level of sophistication, that is based on the accuracy required, two types of models are there, that is screening models and refined models, okay. So the kind of data inputs that are required for a model, atmospheric dispersion model, is the type of the source, then the emissions of each pollutant, then the location and height of the source, and also the stack characteristics. And there are several types of sources. It can be a line source such as vehicles, or it can be a point source such as stacks or chimneys. It can be an area source like treatment ponds, or it can be a volume source like buildings. So actually the prediction depends upon or estimation of pollutant concentration depends upon the type of source also. So equations are actually developed depending upon the type of the source. So the formula or the equation that is developed for a point source cannot be applied for a line source. And this is a basic procedure in an atmospheric dispersion modeling. That is, some set of data inputs are there, and we are providing those data into the atmospheric dispersion model, whether the data will be processed, and in the third stage the output, that is the prediction of atmospheric pollutant concentration, will be the third stage. And after that, in the fourth stage, the data will be analyzed, that is whether there is any ill effect or harmful effect, or what are the potential impact of those pollutant on the ground. Okay, so these are the in four different stages the atmospheric dispersion modeling is conducted. First one is data input, which is given to the atmospheric dispersion model, and within that model the data will be processed, that is stage 2. And in stage 3, data output will be obtained from the model, that is the pollutant concentration will be predicted, that is the pollutant concentration will be predicted. And in stage 4 the data will be analyzed. So there are different types of model: Gaussian plume model, box model, Gaussian puff model, and other nowcasting and forecasting models. Nowcasting means predicting about the present, and forecasting means predicting about the past, predicting about the future. And moving on to Robert's equation. Robert's equation is one of the mathematical equation governing the dispersion of air pollutant in atmosphere, and this equation is actually applicable when there is no pollutant diffusion through the ground surface and the pollutant passes through the YZ plane. Okay, so the formula is rho xyz is equal to q divided by 4 pi x into kyy into kzz the whole raised to 1 by 2 into e raised to minus u bar divided by 4x into y square by kyy plus z square divided by kzz the whole square. Okay, and this is equation number 1. So this equation is known as Robert's equation, and this equation is applicable when there is no pollutant concentration in the ground level and the pollutant is dispersed in the YZ plane. Okay, and here rho is the mass concentration of pollutant, q is the source strength, then kyy and kzz are the diffusion coefficients or the uh, spreading coefficients or the diffusion constants for homogeneous turbulence. And here u bar is the mean wind velocity. And in this equation, actually the above equation was formulated based on the assumption that homogeneous turbulence is prevailing in the atmosphere. So in such a case, but in reality or in the actual condition, atmospheric turbulence will not be homogeneous, that is, or the wind velocity will be varying, so that all parameters will not be uniform. Okay, so when the atmospheric flows are turbulent, instantaneous wind velocity in x, y, and z directions are given by u, v, and w, which are random variables of space and time. Okay, so the instantaneous wind velocities are given by u is equal to u bar plus u dash, v is equal to v bar plus v dash, and w is equal to w bar plus w dash. So here u, v, and w are the instantaneous wind velocity parameters. U bar, v bar, and w bar are the average wind velocity along x, y, and z directions, and u dash, v dash, and w dash are the fluctuating parameters. So when the atmospheric flows are turbulent, all these three parameters have to be considered, that is instantaneous wind velocity parameters have to be considered. And these fluctuating parameters together with molecular diffusion causes the mixing up of the pollutants. And Robert's equation is also applicable when there is no diffusion of pollutant into the surface and the pollutant is completely dispersed in the upper half space, that is when Z is greater than 0. Okay, so when the Z coordinate is greater than 0 and when there is no diffusion onto the surface, use the formula rho A is equal to q divided by 2 pi x into kyy into kzz the whole raised to 1 by 2 into e raised to minus u bar divided by 4x into y square divided by kyy plus z square divided by kzz. Okay, so just the only difference between the first equation and this equation is that q divided by, in the previous equation it was q divided by 4 pi x and in this equation it is q divided by 2 pi x, only that difference is there, and all the parameters are just the same as the previous equation. Rho stands for mass concentration of pollutant, q stands for source strength, kyy and kzz are the diffusion constants, u bar is mean wind velocity, and x, y and z are the coordinates. So Robert's equation is actually not a 100%. It will not give accurate 100% results. Will not be given by this Robert's equation. That is, accurate results will not be obtained. Why? Because one of the main assumption in developing this equation was homogeneous turbulence, the homogeneity of turbulence that is prevailing in the atmosphere. But you know that in the actual condition turbulence will not be homogeneous, especially in the vertical direction. So this Robert's equation being as it has some drawbacks regarding the various assumptions that are used in developing this equation. Another model was developed based on this Robert's equation, and that was Gaussian plume model. And Gaussian plume model is one among the various steady state model. Okay, so Gaussian plume model is one of the air pollution model that is widely used nowadays. So all the drawbacks of this Robert's equation was rectified by developing this Gaussian plume model. Okay, so in this session we have discussed about the air pollution models, the different types of models, the various segments of an elevated plume, and also about Robert's equation. Hope you understood this session.